We'll now look at the idea behind segments and rays. We're going to start with 2 points, A and B, that are distinct, and L is going to be any line that contains them. We're going to start by defining the segment that's joining A and B. So the segment is the set of all the points on the line such that either P is equal to A, P is equal to B, or A, P, B. So it can be A is part of the segment, B is part of the segment, and all of the points between them are part of the segment. We call the points A and B endpoints, and all of the other points we call them interior points. Here's what a segment looks like on a sphere. It's just a little piece of this great circle. The next thing we want to define is the idea of a ray. In particular, we're going to look at a ray that from A through B. So the ray is going to be the set of all points P on my line L, such that either P is equal to A, P is equal to B, P is between A and B, or B is between A and P. So essentially the idea, in Euclidean, I have a point A and a point B, so I'm going to include these on the ray. I'm going to include all the points between them, so that would be the line segment, and all of the points past B, and that would be my ray. We call our point A the end point, and all of the other points are going to be the interior points. Here's a picture of a ray on a spherical segment, so this would be going from A through B and up through C, so this point D on the back is actually not part of the ray, since the betweenness relation here would be DAB instead of ABD. So spherical rays are essentially like semicircles, little half circles on the sphere. So now that we're done with that, let's consider a quick question. In Euclidean space, if we know ABC holds, then there's a point D such that ABCD. Essentially what that says is we can always find a point further down the line. And I want to know, is this true in spherical geometry as well? And the answer is, in spherical geometry, no. So let's look at a circle for our line. If we have A here, and we put C as its exact polar opposite, B can be any point here, we can never find a D that's further along, because if I, for instance, put a D here, then I don't have that it's true that ACD. Instead, I have ADC. So in spherical geometry, this no longer works. And this is going to give us the idea for our next axiom, axiom 5. Axiom 5 states that if I have any 4 distinct collinear points A, B, C, D, and I know that ABC, then we have either that DAB, ADB, BDC, or BCD. So I'm going to draw exactly what this is saying in the Euclidean space, and then I encourage you to draw a circle and see how it works on a circle in the spherical geometry. So I'm going to start with a number line. We have 3 points we know, A, B, C. So now I have to consider this 4th point, D. It could go over here, in which case DAB. It could go somewhere in here, in which case we have the ADB holds. It could go somewhere between B and C, in which case BDC, or it could move over here, BCD. And those are the only 4 cases of where D can go. Like I said, I encourage you to draw a circle, put 3 points A, B, C in order, and then look at where D can go and show that one of these 4 things must be true. The next thing we'll look at, if I have the ABC is holding and L is the line of collinearity of ABC, so it's the line that passes through all 3 of them, then it's the union of the 2 rays BA and BC. While I won't give a formal proof of this, I will draw a picture to demonstrate kind of the basic idea of what's happening. So we have a line, and we know that ABC holds, so we know B is in the middle. Well, the ray BA consists of the point B, all the points between B and A. It consists of A, and it consists of all the points beyond A. The ray BC consists of points B and C, all the points between B and C, and all the points beyond. And so we can see that the union of these 2, if we combine them, we do get the whole line. And that's the basic idea of what this theorem is saying. And we call these opposite rays. So any two rays who have a common endpoint and their union is a line are known to be opposite rays.